Yeah, thank you for having me, and happy birthday to Jean-Marc. Obviously, we don't know each other that well yet, but it's lovely to see you. And in part, obviously everyone knows Jean-Marc for the really funky shirts. So I'm really hoping that I've done you justice by it's fantastic. Yeah, so I'm Paul's PhD student, and I'm looking at droplet impacts specifically in the bouncing regime. Kind of today, I'm just going to briefly introduce you to what the dynamics are in the system and how they evolve, and specifically what am I considering within my model. I'm going to talk quite a bit about the pressure and where that kind of sits in, because that's kind of the new bit to what I do, is I consider that air layer, and I'll get onto that in a second. That basically leaves me with three sort of distinct regions, and I'm going to talk to you about matching conditions and how I kind of smush it all together, and then finally show you some pretty pictures. So if you want to just zone out for about 10 to 15 minutes, the videos start soon. It's a lie because the video's on the next slide. I don't have a fancy lab, but I do have a very sunny day in South Wales in August, as you can tell. This is my hometown in Swansea, and it's one of my favorite videos because it really shows the broad range of dynamics that can occur when you talk about bouncing droplets. We have sort of very large drops that cause coalescence and splash jets and cascades of droplets. You have these very, very small ones. I don't know how clear it is. There's a few that appear down here, these really, really millimetric droplets that kind of walk along the surface, more similar to what you saw in the previous talk. And then you get ones that kind of look stationary and eventually just look like they disappear, and that's where they're coalescing. For my work, we're specifically looking at those ones that are an analog to the pilot Faraday system. So we're looking at those very millimetric droplets that cause these small waves cascading out. Nothing quite so fancy as that yet. If you want to know more about that, go talk to Radu. Yeah, so this is kind of the physical interpretation of what we're doing. Me in particular, then, I'm looking at a 2D system. I'm going to restrict motion to vertical for the moment. So we're going to have a droplet that falls straight down, prescribed along the z-axis. The free surface, so we're considering impacts on a deep liquid bath, so essentially infinite depth and infinite domain. Between the droplet and the free surface, we have a layer of air, and we're going to be considering that dynamically. I don't know if I've had too much coffee or not enough coffee, one of the two. Yeah, so we have a liquid droplet, air layer, and a big free surface, and an infinite bath. So there are three kind of very, very distinct regions that exist within the system. So we need three different methods to consider them. Obviously, we start with Navier-Stokes on all of them. I want to get rid of that and make different assumptions on each region to reduce and simplify our model down. Also worth mentioning, we have kinematic boundary conditions and stress balance on both the free surface of the drop and also the free surface of the bath. Bit of housekeeping, I use subscript D, B, and A to mean the droplet, bath, and air. And I do also use L to mean liquid, because in this system, at the very least, the droplet and the bath are both of the same liquid. And I think in the results I have, they are just water. So I'm going to take each of those in turn, starting off with the free surface. Again, thank you so much, Andre. So we're going to follow basically the methods prescribed in the paper that he was talking about. So we start with a weakly viscous liquid filling the negative half plane. And we also have, again, kinematic boundary and stress balance that are prescribed like this, where the PA is the air pressure above, PD pressure below, and surface tension as well. By doing the Helmholtz decomposition, and combining with stress balance, you want to just eliminate that psi, get rid of it, and just have evolution equations for the phi and the eta, so the velocity potential and the free surface. This capital P is kind of similar in that it is the pressure generated acting on the surface above, and I'm going to talk more about that in some number of slides. But basically the pressure is going to keep popping up, but I'm not going to tell you what it is yet. But that's what that is. Next term, surface tension, and then the two on the end are just the viscosity terms. I was going to say that, I think it's already covered. Moving on then to the droplet. For the system that we're in, because we're considering these really, really small drops, we completely disregard gravity. I suppose that was something I probably should mention in this equation, is that there's no gravity for the moment. Not that there can't be, just for the case that we've been looking at, it's unnecessary. So yeah, moving on to the droplet, we were inspired by work done on oscillatory droplets in zero gravity. And yeah, we kind of followed through the methodology of this paper cited at the bottom. So you consider a potential flow inside the drop and assume the free surface is some R0 plus a small perturbation described. Again, kinematic boundary and a pressure match, this PA atmospheric acting in. Also consider surface tension effects. Sorry, can I just grab my water? Thank you. So because we're restricting motion vertically, what that means is essentially hidden back under here is the free surface, and the pressure is going to be acting upwards on the droplet symmetrically from about theta equals 0. And because of that, whenever we do a Fourier decomposition of the potential, but also the free surface, in this case, we just disregard sinusoidal terms. So we only have one set of Fourier coefficients, Cn, to consider. And that will give us the shape deformation as we evolve in time. Yeah, following through this method, you end up with this evolutionary ODE for those coefficients, where we have this lambda is kind of our viscosity, a frequency omega, and the pressure forcing is on the right there. These p hat ends are the Fourier modes of the pressure acting on the droplet, and obviously it's kind of important to note that this is in polar coordinates, whereas the other p on the previous slide, the pressure in the larger system, is in Cartesian. So I'll talk more about how we match those in a minute. So that's our evolutionary equation for the droplet bit in the middle, and this is the fun bit. So obviously, when the droplet is far away from the free surface, the two things aren't talking to each other, and this is where essentially the droplet's kind of in free motion. So either it's falling or flying off into infinity. When they're close to each other, though, they start interacting. And for the sake of this model, we're going to assume that they're close to each other, and I'll talk about switching it on and off in a minute. So when they are close, they are very, 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 very close. If we went back to that video, or you look at any of the videos, they do look like they touch, but what's actually happening is there's a thin layer of air constantly throughout the layer, throughout the interaction. If that air layer were to deplete, the droplet and this free surface would touch, they would coalesce, and it would break my code, and I'd be very sad. So that can't happen. But this height of the air layer is much smaller in comparison to the radius of the droplet or the effective width of the lubrication layer. Spoilers of the air layer, therefore we can use lubrication theory. So essentially we have the free surface of the sphere as an upper bound, the free surface of the bath as a lower bound, and this evolution of the air in the middle. So using this assumption, sorry. Yeah, taking the assumption that the height is much thinner than the air, we end up with a channel flow that we can reduce down. And we end up with Poisson flow for the velocity, a Poisson profile for the velocity. And we can actually derive the thin film equation for the evolution of the height in the air layer. Important bit here is that dxp, so that again pressure keeps popping up now in 3 different equations, and we're going to try and join them together, and this is just derived by taking vertical averaging of conservation of mass. So this is sort of everything I've been working with. I cheekily didn't mention this bit, but this is just the evolution of is just Newton's law for the position of the center of mass of the droplet. And this is the f of t that was in that other equation in Andre's slides, I believe. Very similar sort of thing. So just integral of pressure over the affected area, which in my case is just the length of my lubrication. So obviously, how do we combine them all together? That's with the thin film equation. So we use the thin film kind of as we go through our time stepping, and we evolve these equations at each step. We compute the pressure dynamically using this equation, feed back in, and then move forward in time. I talked a bit about matching, and I'm going to do that now before I go on to the numerics. So there are three parts of this that kind of I got stuck on when I was doing the summary bit. So the first one being, obviously, we have an equation for the sphere in polar coordinates, and we have an equation for the drop, for the bath, and the pressure in Cartesian, matching them together. Because of the regimes that we're looking at, and because we're taking these like small millimetric droplets in small Weber regime, we can assume that the affected area, that lubrication width, is going to be quite small. And it seems to have reasonable success. We're just going to use a small angle approximation. That just makes everything so much nicer to deal with. Next, we have the contact time. So as I said, when the droplet is very far away from the free surface, that we can't really take a lubrication approximation. It doesn't make sense to do so. So when do we kind of switch on and switch off the system? And I'm just going to say when it's close to it. That feels like the most obvious answer, and sometimes it is. So yeah, we impose some epsilon such that when the height of the air layer is sufficiently small, we kind of turn on the lubrication approximation. Outside of that, that droplet is just moving as it was, and the free surface doesn't feel the effects of the droplet. Obviously, that can't work under the entire radius though, so where do we put our boundary for our width? And I'm actually going to use the same condition for that. So at some point along the radius of the drop, the free surface is going to kind of peel away. We assume that, the small interactions with each other, it's not going to get fully submerged. So again, we have this sort of critical value on our horizontal boundary where the height is sufficiently large enough that lubrication approximation doesn't quite make sense. So we just set pressure to be atmospheric and set it to 0 outside of this region. Yes, those are our three sort of tricks to couple everything together. Computing this then numerically, we used full-order Runge-Kutta for the time step evolution and a pseudospectral approach to take the spatial considerations of the equations. And I really wish I'd put in another system for the equations here, but I didn't, so oh well. Yeah, onto the pretty pictures. So what does this look like? Well, we start with the droplet sufficiently far away from the free surface, and this is sort of our evolution in time here. So we have the North Pole center of mass and South Pole of the drop falling through time, and you can see they're just in free fall for a sufficiently long time. They eventually interact. I promise there is a gap between those two lines there, and then it does lift off again, and you can see the oscillation. Video then. In blue, you have the free surface, and it will loop around, so don't worry if you're confused. The blue solid line is the free surface. The dashed line is the south pole of the sphere, or the south of the sphere. The red is the pressure calculated at each time step that is then fed back into the system. And the vertical black lines are just my boundary for the lubrication regime. So outside of this, basically nothing is happening except the free surface and velocity potential keep being computed for the full domain. The reason that I kind of zoom in on this region is because in order to not get any rebound, so because we take pseudospectral, there is a periodic boundary there. Numerically, we just set the domain to be absolutely massive. I think it's 64 times the radius, just so that we don't have to worry about waves traveling back and interacting with the system. And as you can see, it will just keep flying off to infinity if we leave it alone. So that's quite fun. That background. Yeah, and the nice thing about this video is you can really see like where the pressure effects start interacting with the system. So whilst you get initial impact, you get this very sharp spike to start, and then eventually the pressure profile does like level off, creating this like near flat surface-ish for most of the impact. And then eventually, as it starts to slow down and rebound, it changes shape slightly, and you get these weird regions of negative pressure where you get this pinching effect, whereas the droplet pulls the free surface up with it. And then it eventually disappears. Looking then in a bit more detail, we have information gathered about the height of the air layer. So this is just the difference between the free surface of the sphere and the free surface of the droplet. It's not potentially the most clear, but that's what the second photo is for, where the width here is the full radius, so 0 to R, and the black line kind of highlights the region where we're computing the lubrication layer. So it really does not go out to the full radius, but about 1.2-ish at widest, and that's as it's moving down. As it starts to rebound upwards, the lubrication layer does shrink again. And you can see that in a bit more detail, where I just set everything outside of that to 0. Contrast to that, then you can look at the pressure. So again, this is what's computed through the thin film equation, but also the effect of surface tension on the drop on the bath is affecting the drop as well. So this is again pressure for the full-time evolution underneath the radius, and you can see it's 0 outside of our lubrication area, lubrication regime. And I've just taken 4 time slices, so you can kind of get a good comparison of the pressure profiles. And they seem to kind of correlate to these 4 kind of distinct regions that we see in the dynamics. So you get the initial contact with a sharp spike, you get the kind of, I need a better word than depression, but the depression of the droplet as it's kind of moving with the bath constantly downwards. You get the pinch off where the droplet is pulling away and pinching at the free surface on either side. And you get this like quite nice little peak thing on the black line happening there on either side of the lubrication regime. And then finally the release, as it's moving away, you get this weird sharp spike of negative pressure just as it pulls it away. One thing that I found particularly interesting when I first started doing this work, we kind of took this work done by Carlos and Paul on solid hydrophobic spheres, as we consider that to be quite a good approximation for a liquid sphere. At the very least, within the work that I've been doing, the matching was never quite right. And we realized the potential deformation was the bit that we were missing. And it seemed to work. So you do get this. All I've done here is just switch the Fourier modes of the droplet to 0, make it effectively solid, and you do see quite a sharp difference in the numerics. This has all been done for one specific regime, so a specific value of R and specific value of W, all of these pictures matched. But if we start looking at expanding that and seeing how it affects the wider regime, I just took, for the minute, 3 different values of R and 4 different initial speeds and non-dimensionalize them. So you can kind of see this is the non-dimensional time. So all droplets will hit at time 1. And then as it rebounds, sorry, as it rebounds, you can see the evolution. And then when it flattens off, that's it in the opposite of free fall, moving upwards. I don't know if free fall has an opposite, but doing that. And you can see that as the Weber number increases, you have a longer impact time. The other image then is the coefficient of restitution. And you can see for small Weber numbers, it seems to be lower and it has this nice curve shape. And that kind of matches, at the very least preliminarily, with work done by Radu, Alventosa and Harris, where you do see this sort of behavior. This is very, very off the press. So yeah, we still need to do more testing here, but I'm very happy with these pictures, so I hope you are too. And then finally, this is just to show you the deformation of the droplet and how it switches and bounces throughout the progress. So this is just point of impact to point of release on the specific case that I showed you on all of the previous pictures. Just rounding off then, the kind of 2 kind of key takeaways from, at the very least, I think, of this work, is that the pressure, if we compute it dynamically as we do these sort of bouncing droplet phenomena, you do get a good match with what people have been doing for ages. So it turns out you guys were on the right track for quite a lot of this. And yeah, it does sort of match this top hat profile that people have been using. And also the deformation of the droplet is actually quite important, turns out. Moving on forwards, preliminarily, we've started looking at comparisons with DNS, and we do want to do more of them. And we've only just done, again, 15 runs of changing some values, so we do need to do a better sensitivity test, as well as look at mesh refinements, other scientific computery things. but those are both in the works, and hopefully we'll get some even nicer results down the line. Potential extension that we're interested in is looking at 3D and how that would affect it, and also potentially if we consider oblique impact, so allowing that droplet to move, not just restricting to the vertical, how that affects the pressure profile, because a lot of the assumptions that we make do assume symmetry. So it'd be interesting to see what changes could be done would the assumptions that we make still work. I will stop taking up your time now. Thank you.
Good.